stars appear permanent. They are, for most people, the most unchanging things the eye will ever rest upon. On any clear night, they return to the same positions, the same shapes, the same faint and patient glow that someone standing in this exact place 1,000 years ago would have recognized without the slightest hesitation. There is a particular kind of comfort in that. Whatever else may shift or unsettle in the course of a single life, the stars remain where they were. They hold their places tonight the same way they held them last night, and they will hold them again tomorrow, with a quiet consistency that asks nothing of the person watching them. Ancient navigators trusted them enough to cross open oceans in wooden boats, steering by nothing more than the angle of a few reliable stars against the horizon. Farmers watched which constellations rose at dusk and built their planting calendars around patterns that had repeated faithfully for longer than any civilization could measure. The stars were not understood. They were simply relied upon. And that reliability was enough. None of those early observers knew what a star actually was. They did not need to. What mattered was that the sky could be read. That certain lights appeared at certain times. That the heavens, unlike nearly everything else in human experience, could be counted on not to change. Even now, in an age when their nature is far better understood, that feeling endures. A clear night sky still offers something difficult to find elsewhere. A sense of steadiness. A quiet assurance that some things are older than any worry you carry tonight, and will continue long after every present concern has gently dissolved. But there is something the eye tends to pass over on a night like this. Something between the stars that carries no light of its own and therefore draws no attention. Darkness. Not the darkness of absence. Not emptiness waiting to be filled. But a darkness that holds within it something so faint, so diffuse, so thinly spread across such enormous distances, that no human eye will ever perceive it directly. The space between stars is not vacant. It is occupied by gas and dust, scattered so thinly that a cubic centimeter of this material might contain only a handful of atoms. On Earth, even the most carefully produced laboratory vacuum holds far more matter than this. By any ordinary standard, these stretches of space would qualify as empty. And yet they are not. Across distances measured not in miles or kilometers but in light years, those sparse particles accumulate. Slowly, across scales the mind can hold only loosely, they gather into structures of extraordinary size. Clouds of gas, composed predominantly of hydrogen, the simplest atom in existence, nothing more than a single proton attended by a single electron, drift through the galaxy in formations so vast that light itself requires decades, or centuries, to cross from one edge to the other. These clouds are called molecular clouds. And they are among the most important places in the universe, though nothing about them suggests importance in any way a person would normally recognize. They are cold. Their internal temperatures linger only a few degrees above absolute zero, the lowest temperature that physics allows. They are dark. In their densest regions, they absorb and block the light of every star behind them, casting vast silhouettes against the softer glow of the galaxy beyond. And they are extraordinarily patient. Nothing about them suggests motion, or urgency, or any of the qualities a person might associate with creation. They simply drift. They persist. They wait, sometimes for millions of years, in no particular hurry. This is where stars are born. Not in heat. Not in light. Not in any of the conditions one might expect for the origin of something as luminous and powerful as a star. But here. In the coldest, darkest, most silent places the universe contains. Light begins in darkness. This is not a metaphor offered for beauty's sake. It is a physical description of what happens. And it is the opening line of a story that stretches across billions of years, passes through every element on the periodic table, and arrives, in its own patient time, at the atoms that compose the body of every person who has ever lived long enough to look upward and wonder. The story of a star is not a distant one. Every breath you draw tonight pulls in oxygen that was forged inside a star. The carbon that forms the structural backbone of every molecule in your skin and muscle and bone was assembled in a stellar core burning at millions of degrees. The iron that is, at this very moment, carrying oxygen through your bloodstream was built in the final hours of a star that lived and died long before the sun existed. These are not dramatic claims made for effect. They are settled, physical truths. And tonight, there is time to follow how it all happens. From the very beginning. Slowly. With nowhere else to be. A molecular cloud can persist for millions of years in a state of quiet equilibrium. Internal pressure, the gentle outward push of gas molecules moving within it, holds it against its own gravity. The cloud does not collapse. It does not ignite. It simply drifts, balanced between two opposing tendencies, in a patience that makes geological time seem brisk. But that balance is delicate. And the universe, over long enough timescales, does not leave delicate balances undisturbed. Sometimes the disturbance comes from outside. A shockwave from a distant supernova, the explosive death of another star, ripples through the interstellar medium and compresses a region of the cloud just enough to tip the balance. Sometimes a density wave, rolling slowly through the spiral arm of the galaxy, squeezes the gas as it passes. Sometimes two clouds drift close to one another, and their mutual gravity nudges a pocket of gas past the threshold of stability. The cause varies. The result is the same. A small region of the cloud begins to collapse under its own gravity. Not suddenly. Not dramatically. The process unfolds over hundreds of thousands of years, and in its earliest stages it would be invisible to any instrument. Gas drifts inward. Dust follows. The region grows denser, and as it grows denser, its gravitational pull strengthens, drawing in still more material from its surroundings. This is gravity at its most patient. It does not seize. It does not wrench. It gathers. Slowly, persistently, with a gentleness that belies the scale of what it is building. And what it is building, grain by grain and atom by atom, is a star. As the collapsing region contracts, something else begins to happen. The gas, pressing inward under gravity, compresses. And compression, in any gas, produces heat. The center of the collapsing cloud begins to warm. Not by much, at first. Not enough to glow. But the temperature rises, degree by degree, century by century, as the material continues to fall inward. What forms at the center is called a protostar. It is not yet a star. It does not yet sustain nuclear fusion. It is simply a dense, warming knot of gas, growing gradually hotter as gravity continues to feed it material from the surrounding cloud. But it is, in a sense, a promise. A structure on its way toward becoming something else entirely. Around the protostar, the infalling material does not arrive in a straight line. Because the original cloud possessed even the slightest rotation, conservation of angular momentum causes the inflowing gas to flatten into a spinning disk, a protoplanetary disk, a broad, slowly turning sheet of gas and dust that surrounds the young protostar like a vast, gentle wheel. This disk is not incidental. It is the birthplace of planets, moons, asteroids, and comets. The seeds of a solar system are planted here, alongside the star itself, in the same slow gathering of matter that gave the star its start. This process is not rare. It is happening right now, in this galaxy, in thousands of places simultaneously. The Orion Nebula, visible to the unaided eye as a faint smudge of light below Orion's belt, is one such place. Within it, new protostars are forming at this very moment, each one surrounded by its own spinning disk, each one following the same quiet process of gravitational gathering that has produced every star the universe has ever contained. As you rest tonight, stars are waking up. Not metaphorically. Physically. In nurseries scattered across the galaxy, gravity is drawing gas inward, cores are warming, and the conditions for something luminous are being quietly assembled. But the protostar is not yet finished. Gravity continues to compress its core. the temperature continues to climb. Thousands of years pass. Hundreds of thousands. The core grows hotter, denser, more pressurized. And then, when the temperature at the very center reaches approximately 10 million degrees, something remarkable happens. The hydrogen nuclei at the core, protons, stripped of their electrons by the tremendous heat, begin to move fast enough to overcome the electromagnetic force that normally repels them from one another. They collide. They merge. For hydrogen nuclei fuse together to form a single helium nucleus, and in the process, a small amount of mass is converted directly into energy. This is nuclear fusion. This is the moment a star is born. It is not an explosion. It is not a sudden burst of violence. It is a kindling. A threshold crossed. A slow warmth becoming, at last, a sustained and radiant glow. From this moment forward, the star will shine. Not for days. Not for centuries. But for millions or billions of years, depending on how much material it gathered in its cradle. Light has appeared in darkness. Not from outside. Not delivered from elsewhere. But generated from within, by the patient work of gravity pressing simple hydrogen together until the atoms themselves began to merge. This is what a star is. Not an object placed in the sky. Not a fixed point hung in the dark. But a process. A sustained event. A place where gravity and fusion hold each other in a balance so patient, so enduring, that it can persist for longer than the human mind can comfortably hold. And this is only the beginning. If you have just found this channel, you are welcome here. This is a quiet place, built for evenings exactly like this one. If you feel like it, leave a comment and share where you are listening from tonight. It is always a gentle thing, knowing that others are resting under the same sky. With fusion ignited and the birth cloud slowly dispersing, the star enters the longest chapter of its existence. This phase is called the main sequence, and it is defined not by drama or transformation but by something far less conspicuous. Balance. Two forces now govern the star's behavior. The first is gravity. It has not stopped working. It continues to pull the star's vast mass inward, pressing every particle toward the center, attempting to compress the entire structure into the smallest possible space. Left unchecked, gravity would collapse the star entirely. But it is not unchecked. The second force is radiation pressure, the outward push generated by the energy of nuclear fusion in the core. Every fusion reaction releases energy that works its way outward through the star's interior, and that energy exerts pressure on the layers above it, pressing them outward, resisting gravity's inward pull. These two forces, gravity pulling in, radiation pushing out, settle into a precise and patient equilibrium. Neither wins. Neither relents. They hold each other in a balance so finely tuned that the star's size, temperature, and luminosity remain essentially constant for millions or billions of years. This balance is called hydrostatic equilibrium. It is not a battle. It is not a struggle between opposing enemies. It is better understood as a conversation, an ongoing negotiation between two fundamental tendencies, each one necessary, each one shaping the other, each one content to continue the conversation for as long as there is fuel to sustain it. And the fuel, for a main sequence star, is hydrogen. Deep in the core, where the temperature holds steady at roughly 10 to 15 million degrees, hydrogen nuclei continue to fuse into helium through a sequence of steps known as the proton-proton chain. This name simply describes what happens. Protons, the nuclei of hydrogen atoms, collide and combine, step by step, until four of them have merged into a single helium nucleus. In each completed cycle, a small fraction of the original mass is not carried into the helium. It is converted directly into energy, following the relationship first described by Einstein, that energy and mass are interchangeable, related by the speed of light squared. The numbers involved are staggering, though they are best received gently. The Sun converts roughly 600 million tons of hydrogen into helium every second. Of that, approximately 4 million tons of matter are transformed into pure energy each second. And yet the Sun contains so much hydrogen that it can sustain this rate of conversion for approximately 10 billion years before the supply begins to meaningfully thin. The energy produced in the core does not reach the surface quickly. This is one of the more quietly astonishing details of a star's inner life. A photon of energy born at the center of the Sun does not travel in a straight line to the surface. It is absorbed almost immediately by the dense surrounding material, then re-emitted in a random direction, then absorbed again, then re-emitted again. This process, absorption, emission, repeats countless times as the energy slowly migrates outward through the radiative zone, the dense inner region of the star where energy moves by this patient, scattering process. The journey takes, on average, roughly 170,000 years. The energy that reaches the Sun's surface today, the light that streams outward into space and crosses 150 million kilometers to arrive at the Earth in just over 8 minutes, that energy was born deep in the core approximately 170,000 years ago. It has been working its way outward, step by scattered step, for longer than modern humans have existed. If you felt warmth on your skin earlier today, sunlight on your face, on your hand, on your shoulder, you were feeling energy that began its journey before the last ice age ended. Light that was already old when the earliest human civilizations were still tens of thousands of years in the future. It arrived, after all that time, at precisely the right moment to be felt by precisely the right person. There is no intention in this. Just patience, and distance, and the steady workings of physics across spans of time that resist easy comprehension. Not all stars burn the way the Sun does. This is one of the more important distinctions in stellar physics, and it follows from a single factor decided at the moment of a star's birth: its mass. Mass is destiny, in the life of a star. How much material a star gathers during its formation, how much gas and dust gravity manages to collect before the remaining birth cloud is dispersed, determines almost everything that follows. The star's temperature, its color, its brightness, how long it will live, and how it will eventually die. All of this is set, in broad terms, from the beginning. A star born with significantly more mass than the Sun will burn far hotter. Its core temperatures will be higher, its fusion reactions more intense, and its surface will glow blue-white with a fierce, radiant energy. But that intensity comes at a cost. A massive star consumes its hydrogen fuel at a vastly accelerated rate. Where the Sun will burn steadily for 10 billion years, a star 10 times its mass might exhaust its core hydrogen in only 20 million years. Brilliance, in the stellar world, is brief. A star born with less mass than the Sun follows the opposite path. A red dwarf, a star with perhaps a tenth or a fifth of the Sun's mass, burns so coolly and so efficiently that its fuel will last not for billions of years, but for trillions. These are the dimmest stars in the galaxy, so faint that not a single one is visible to the unaided eye, despite the fact that they are the most common type of star in existence. A red dwarf born in the early universe, shortly after the first generation of stars appeared, would still be burning today, barely diminished. It will continue burning long after the Sun has completed its own life and gone dark. There is something gently striking about this. The brightest stars are the most fleeting. The faintest are the most enduring. The universe does not reward intensity with longevity. It rewards restraint. The Sun sits between these extremes. It is a middle-mass star, burning at a middle temperature, glowing a warm yellow-white. It is roughly 4.5 billion years old, which places it near the midpoint of its expected main sequence lifetime. You are alive, in other words, at roughly the halfway point of your own star's story. There is as much time ahead of the Sun as there is behind it. This is not a fact that demands anything. It simply is. A quiet coordinate in a much longer journey. There is one more quality of a main sequence star that deserves a moment of stillness. Stars are not silent. Not in the way a person might hear sound on Earth. there is no air in space to carry vibrations from star to listener. But within their interiors, stars vibrate. Pressure waves ripple through the dense gas, bouncing and reflecting off internal layers, creating patterns of oscillation that are as distinctive as a fingerprint. These oscillations can be measured from Earth, with great precision, by watching the tiny fluctuations they produce in a star's brightness and surface motion. The study of these vibrations is called asteroseismology, a word built from the Greek for star, for earthquake, and for law. It allows scientists to probe the interior structure of stars in much the same way that geologists use seismic waves to study the interior of the Earth. Every star has its own pattern of oscillation, its own set of frequencies, its own quiet music, playing steadily in the deep interior, inaudible but measurable, present but unseen. Every star has its own song. The sun has been singing its particular arrangement for 4.5 billion years. This is the main sequence. The longest chapter. The steadiest phase. A star in hydrostatic equilibrium, converting hydrogen into helium with a patience that spans ages, holding its size and brightness constant against the dark while, deep in its core, an almost imperceptible change is taking place. The hydrogen is thinning. Not quickly. Not urgently. But with each passing million years, the proportion of hydrogen in the core decreases, and the proportion of helium increases. The core grows slowly richer in the heavier element and slowly poorer in the fuel that sustains the fusion reactions keeping the star alive. This change is so gradual that it takes billions of years to produce a noticeable effect. But it is happening. And it cannot be reversed. The star is not aware that its fuel is finite. It has no mechanism for conserving its reserves. It simply burns at the rate its mass demands, and the balance that has held for so long continues to hold, and the light continues to shine, steady and even and seemingly permanent. But equilibrium, no matter how patient, cannot last forever. If this kind of slow, unhurried exploration feels worth returning to, a subscription costs nothing and simply means that more evenings like this one will find their way to you. There is no rush. There never is here. The change, when it finally becomes significant, does not announce itself at the surface. For a long time, the star looks the same, shines the same, occupies the same place in the sky with the same apparent permanence it has always carried. But in the core, the situation has quietly shifted. The hydrogen in the central region, the very heart of the star, where temperatures and pressures are highest and fusion has been most active, has been substantially consumed. What remains is predominantly helium. And helium, at the temperatures currently present in the core, does not fuse. It simply sits there, inert, accumulating, growing denser as more of it is produced by the ongoing fusion in the layers just above. This is not a crisis. It is a transition. But it is a transition that changes everything. With the hydrogen in the central core depleted, fusion there slows and eventually ceases. The core, no longer generating the energy that was pushing outward against gravity, begins to contract. Gravity, patient as ever, pulls the core material inward, compressing it into a smaller, denser space. And as it compresses, the core heats up, not from fusion, but from the conversion of gravitational energy into thermal energy. The same principle that warmed the protostar during its initial collapse is at work again, on a smaller scale but with significant consequences. The rising temperature in the contracting core has an effect on the material just above it. Hydrogen still exists in a shell surrounding the helium core, hydrogen that was previously too far from the center to participate in fusion. Now, heated by the contracting core beneath it, this shell of hydrogen reaches fusion temperatures and begins to burn. This is called shell burning. It is not the same as the steady core fusion of the main sequence. It is more intense, more energetic, and it produces a dramatic change in the star's structure. The enormous energy produced by hydrogen shell burning pours outward into the star's envelope, the vast outer layers of gas that make up most of the star's volume. This energy pushes those layers outward, and they respond. They expand. Slowly, over millions of years, the star swells. In the case of the Sun, this expansion will eventually carry the outer surface to perhaps 100 to 250 times its current diameter. A star that today fits comfortably in the center of its solar system will one day reach outward past the orbit of Mercury, past Venus, and perhaps to the very edge of Earth's current path around it. As the outer layers expand, they also cool. The surface temperature drops, and the color of the star shifts, from the warm yellow-white of its main sequence life to a deeper amber, and then to red. The star has become a red giant. Not through an explosion, not through any sudden or violent event, but through a slow, structural transformation driven by the quiet depletion of fuel in its core. This is not decline. It is not deterioration in any meaningful sense. It is change. The star is becoming something different, and in doing so, it is entering one of the most creatively important phases of its entire existence. Because deep in the core of the red giant, something new is about to begin. The helium that has been accumulating, the product of billions of years of hydrogen fusion, is now being compressed and heated by the ongoing contraction of the core. When the core temperature reaches approximately 100 million degrees, 10 times hotter than the hydrogen fusion that sustained the star for most of its life, the helium nuclei begin to fuse. 3 helium nuclei combine to form a single nucleus of carbon. This process is called the triple alpha process, named for the fact that helium nuclei are also known as alpha particles, and 3 of them are required for each reaction. It is a delicate process, one that depends on a particular resonance in the carbon nucleus that allows the reaction to proceed at a meaningful rate. Without that resonance, a feature of nuclear physics that could, in principle, have been different, carbon would be vanishingly rare in the universe, and the chemistry of life as it exists would not be possible. Carbon is not the only product. Further reactions between helium and the newly formed carbon nuclei produce oxygen. These 2 elements, carbon and oxygen, are the primary outputs of helium fusion in the cores of red giants. And they are, not by coincidence, 2 of the most essential elements for life as it is known on Earth. The carbon in your body was built this way. Through the triple alpha process, in the core of a red giant that lived and died long before the sun was born. Every carbon atom in every cell, every protein, every strand of DNA, all of it was forged at temperatures of 100 million degrees, deep inside a star that no longer exists. The oxygen you are breathing right now was assembled alongside it. Built in the same stellar core, through the same sequence of nuclear reactions, scattered into space when that star reached the end of its life, and eventually gathered into the cloud of gas and dust that collapsed to form the Sun and its planets 4.5 billion years ago. This is worth pausing with. Not because it is dramatic, but because it is true. You are not merely observing the universe from a comfortable distance. You are made from it. Assembled from materials that were manufactured inside stars across billions of years. The boundary between you and the cosmos is not as clear as it might feel. There is no boundary, in fact. There is only continuity. For stars more massive than the Sun, the story of element building does not end with carbon and oxygen. It continues. In the cores of the most massive stars, those born with 8 or more times the mass of the Sun, the temperatures and pressures climb high enough to fuse carbon into neon. Then neon into more oxygen. Then oxygen into silicon. Then, in the final stage, silicon into iron. Each successive stage burns hotter and shorter than the one before it. Carbon burning may last 1,000 years. Neon burning, perhaps a few years. Oxygen burning, a matter of months. And silicon burning, the final stage, lasts roughly 1 day. A single day, after a lifetime of millions of years. The star builds itself into a layered structure, with concentric shells of different elements surrounding an ever denser, ever hotter core. And then it reaches iron. Iron is different. It is the most tightly bound nucleus in nature, meaning that fusing iron into heavier elements does not release energy. It requires energy. It absorbs it. For every previous element, fusion was a source of outward pressure, energy that could push against gravity and help hold the star up. With iron, that source disappears. When the core of a massive star becomes iron, the star has reached the end of its ability to sustain itself. The fuel that has powered it through every stage of its life, from hydrogen through helium, through carbon, through silicon, has finally run out. There is nothing left to burn. Nothing left to push back against the gravity that has been patiently waiting, pressing inward, for the star's entire existence. This is the threshold. What happens next, whether the star's ending is gentle or fierce, quiet or generous, depends on something that was decided long ago, in the cold interior of a molecular cloud, when gravity first began to gather gas and dust into the knot that would become this star. It depends on mass. How much matter the star collected in its cradle, all those millions of years ago, now determines everything about how it will leave. A star born with modest mass will depart gently, an exhalation, a slow release, a fading glow. A star born with greater mass will end in a moment of extraordinary generosity, scattering everything it ever built across light years of space in a single, luminous farewell. Both endings are part of the same story. Both are acts of returning. And both leave the universe richer than they found it. For a star born with a mass below roughly 8 times that of the Sun, the ending is not sudden. It is not violent. It is, in its own way, one of the most graceful events in all of nature. A star like the Sun will never build an iron core. Its mass is not sufficient to drive temperatures high enough for the successive stages of heavy element fusion that occur in the most massive stars. Instead, after the helium in its core has been largely converted to carbon and oxygen, the fusion process is slow. The core contracts further, growing hotter and denser, but not hot enough to ignite carbon fusion. The star has reached the limit of what its mass allows. What follows is not a collapse. It is an exhale. The outer layers of the star, no longer gravitationally bound with sufficient strength, begin to lift away from the core. They do not explode outward. They drift. In slow, pulsing waves, thermal pulses driven by the last irregular flickers of shell burning, the star sheds its outer envelope into space. Layer by layer. Breath by breath. The material that once formed the body of a living star now expands outward into the surrounding darkness, carried by a gentle stellar wind. What forms from this shedding is called a planetary nebula. The name is a historical accident. Early astronomers, observing these objects through small telescopes, thought they resembled the disks of planets. They have nothing to do with planets. They are something else entirely. Something far more beautiful. A planetary nebula is the visible record of a star's final exhalation. The shells and rings of gas glow because they are illuminated from within by the fierce ultraviolet radiation of the exposed core, the hot, dense remnant left behind after the outer layers have departed. The colors are not painted on. They are produced by specific atoms in the nebula responding to that radiation. Oxygen glows green and blue. Hydrogen glows red and pink. Nitrogen adds deeper reds. The result is a structure of extraordinary, quiet beauty, among the most visually striking objects in the entire cosmos. These nebulae do not last forever. Over tens of thousands of years, the expelled gas continues to expand and thin, eventually dispersing into the interstellar medium and becoming indistinguishable from the general material between the stars. The beauty is temporary. But then, in the universe, most beauty is. That does not diminish it. It simply places it in time. What remains at the center, after the outer layers have gone, is the core. Stripped bare. Compressed. Extraordinarily dense. This remnant is called a white dwarf, and it is one of the strangest objects you will ever encounter in a quiet study of the cosmos. A white dwarf is roughly the size of the Earth. But it contains approximately the mass of the Sun. This means its density is almost beyond ordinary comprehension. A single teaspoon of white dwarf material would weigh somewhere between 5 and 15 tons. If you could somehow bring a sugar cube-sized piece of it to Earth, it would be heavier than a large truck. The white dwarf is no longer fusing anything. Its nuclear life is over. It shines not because of any ongoing energy production, but simply because it is still hot, residual heat from its former life as a star, radiating away slowly into space. What prevents it from collapsing further under its own enormous gravity is not thermal pressure, and not radiation from fusion. It is something different, a quantum mechanical effect called electron degeneracy pressure. At the densities inside a white dwarf, the electrons in the material are packed so tightly that a fundamental principle of quantum mechanics, the Pauli exclusion principle, which forbids two electrons from occupying the same quantum state, creates an outward resistance to further compression. This pressure has nothing to do with temperature. It would persist even if the white dwarf cooled to absolute zero. It is a consequence of the nature of matter itself, operating at scales far below what any human sense can perceive. This is what holds a white dwarf up. Not fire. Not energy. But the quiet stubbornness of electrons refusing to be pushed any closer together. There is, however, a limit. A white dwarf can sustain itself against gravity only up to a certain mass, approximately 1.4 times the mass of the Sun. This threshold is called the Chandrasekhar limit, named for the physicist Subrahmanyan Chandrasekhar, who calculated it in the early 20th century. Below this mass, electron degeneracy pressure holds. Above it, even the electrons cannot resist, and the remnant must become something else entirely. This limit will matter again shortly. The white dwarf has nothing left to burn. It simply cools. Slowly. Across timescales that dwarf the star's original lifetime. Over billions of years, it fades, from white to yellow, from yellow to orange, from orange to a deep, dim red. And eventually, in theory, it will cool completely, becoming a black dwarf, a cold, dark, lightless remnant drifting through space indefinitely, carrying within its crystallized interior the carbon and oxygen that were the last elements it ever made. But the universe is not yet old enough for this final dimming to have occurred. Not once. Not anywhere. Every white dwarf that has ever formed, every one, across the entire history of the cosmos, is still glowing. However faintly, however far along in its cooling, every single one still emits some light. The candles are still lit. The universe is still young enough that none of them have gone out. This is the Sun's future. In roughly 5 billion years, it will exhaust the hydrogen in its core. It will swell into a red giant, its outer layers extending past the inner planets. It will shed those layers into a planetary nebula, one of those glowing, transient structures of colored gas, and at its center, a white dwarf will remain. An Earth-sized remnant of everything the Sun once was, glowing faintly, cooling slowly, carrying its carbon and oxygen into an unimaginably long twilight. The Sun will not explode. It does not have the mass for that. It will simply exhale. And the white dwarf it leaves behind will persist, quietly dimming, for far longer than it ever shone brightly. Even in ending, there is patience. For stars born with greater mass, those above roughly 8 times the mass of the Sun, the ending follows a different path. It is not gentle. But it is, in its own extraordinary way, generous. These are the stars that build iron in their cores. The stars that fuse element after element in increasingly rapid succession, constructing their onion-layered interiors over millions of years, until they reach the one element that cannot sustain them. Iron. The element that absorbs energy rather than releasing it. The element that marks the end of the line. When the iron core of a massive star reaches a critical mass, roughly 1.4 solar masses, the same Chandrasekhar limit that governs white dwarfs, it can no longer support itself. Electron degeneracy pressure, which holds up a white dwarf indefinitely, is here overwhelmed by the sheer gravitational force of the core's mass. The electrons are forced to merge with protons, forming neutrons and releasing a flood of neutrinos. And the core, with nothing left to hold it up, collapses. The collapse is extraordinarily fast. In less than a single second, the iron core, which moments ago was roughly the size of the Earth, compresses to a sphere approximately 20 kilometers across. A structure that took millions of years to build falls inward in a fraction of a heartbeat. There is something in this compression of timescales that deserves a moment of stillness. Millions of years of patient burning. Billions of nuclear reactions, each one carefully balanced, each one contributing its small measure of energy to holding the star up. And then, in less time than it takes to draw a breath, all of it collapses. The contrast is almost too large to hold in a single thought. But it is real, and it is how the universe works. Patience and suddenness, existing side by side. Not contradicting each other. Simply occupying different moments in the same story. The infalling material, the outer layers of the core, still plunging inward at a significant fraction of the speed of light, strikes the now incompressible ball of neutrons at the center and rebounds. A shockwave is born. It begins to move outward through the star. But the shockwave, on its own, is not enough. Simulations have shown, repeatedly and frustratingly, that the shockwave tends to stall. The material it must push through is too dense, too heavy, too resistant. For decades, astrophysicists struggled with this problem. Their computer models could produce the collapse, but they could not produce the explosion. The solution, or at least, the leading candidate for a solution, involves neutrinos. In the moment of core collapse, an almost inconceivable number of neutrinos are produced. Neutrinos are among the most ghostly particles in nature, nearly massless, electrically neutral, capable of passing through entire planets without interacting with a single atom. Under normal circumstances, they are almost impossible to detect. But in the extraordinary conditions of a collapsing stellar core, the density of matter is so extreme that even neutrinos begin to interact. A small fraction of their energy is deposited in the material behind the stalled shockwave, and this energy, gentle by any ordinary standard, but enormous in aggregate, may be enough to revive the shock, pushing it outward with renewed force. Only recently have three-dimensional supercomputer simulations begun to successfully model this process from collapse through to explosion. But the full picture remains incomplete. There are details that do not yet resolve cleanly. Parameters that remain uncertain. This is not presented as a failure of science. It is presented as science in the act of working. The story is still being told. The understanding is still arriving. And that is how it should be. When the shockwave finally tears through the outer layers of the star and blows them into space, the result is a core collapse supernova. For a brief period, days to weeks, the explosion outshines the entire galaxy in which the star resides. Billions of stars, and for a moment, this single dying one burns brighter than all of them combined. But this brightness is not the most important thing about a supernova. What matters most is what it carries. The outer layers of the star, now expanding outward at a significant fraction of the speed of light, contain every element the star forged over its entire lifetime. Carbon, oxygen, neon, silicon. All of it, scattered across light years of space in a single, luminous release. And in the supernova itself, in the extreme temperatures and pressures of the explosion, elements heavier than iron are created for the first time. Gold, platinum, uranium. Elements that no star, no matter how massive, could produce through steady fusion. These heaviest elements are forged through a process called rapid neutron capture, or the R process, a sequence of reactions so fast that they can occur only in the few seconds of a supernova explosion or in the collision of neutron stars. This is the supernova understood not as destruction, but as generosity. The most powerful explosion in the natural world is also the most creative act. Without supernovae, the universe would contain only hydrogen and helium, the two elements produced in the first few minutes after the Big Bang. No carbon. No oxygen. No nitrogen, no calcium, no iron. No rocky planets. no liquid water. No chemistry complex enough to produce a single living cell. Everything heavier than helium exists because a star made it. And most of it was delivered to the cosmos by a supernova, in the final moments of a massive star's life. The iron that is, right now, carrying oxygen through your bloodstream was forged in the last day of a dying supergiant. The calcium in your bones was assembled in the final stages of stellar nucleosynthesis. Every breath you take draws in oxygen built inside a star. You are not separate from this process. You are a product of it. Made from the generous remains of stars that completed their journeys long before you arrived. What remains after the supernova depends, once again, on mass. If the remnant core is below approximately 3 solar masses, it settles into a new equilibrium, not supported by electron degeneracy pressure, which has been overcome, but by neutron degeneracy pressure. A similar quantum mechanical effect, but operating at a deeper level, among the neutrons themselves. The result is a neutron star. A neutron star is approximately 20 kilometers across, roughly the size of a city. But it contains 1 to 2 times the mass of the Sun. The density is beyond ordinary imagination. A teaspoon of neutron star material would weigh approximately 1 billion tons. More than every building, every vehicle, every human being on Earth combined, compressed into a volume smaller than a sugar cube. Some neutron stars rotate rapidly, remnants of the angular momentum of the original star, now concentrated into a body millions of times smaller. These rotating neutron stars emit beams of radiation from their magnetic poles, and if those beams happen to sweep across Earth's line of sight, they appear as regular, repeating pulses of light. These are called pulsars. Some rotate hundreds of times per second, with a regularity so precise that they rival the best atomic clocks on Earth. Others, called magnetars, possess magnetic fields trillions of times stronger than Earth's. These are among the most extreme objects in the known universe, and the physics governing their interiors remains deeply uncertain. What exists at the very center of a neutron star is one of the open questions in modern physics. The matter there is compressed to densities so extreme that it may exist in states found nowhere else in the universe: quark matter, strange matter, exotic phases of nuclear material that no laboratory on Earth can replicate or observe directly. The interior of a neutron star is, in some respects, as mysterious as anything in the cosmos. We know what surrounds it. We can measure its mass, its spin, its magnetic field. But what lies at its heart remains a quiet unknown. If the remnant core is above roughly 3 solar masses, even neutron degeneracy pressure cannot hold. There is no known force in physics that can resist gravity at this point. The core collapses entirely, and what forms is a black hole. A black hole is not a hole in the ordinary sense. It is not an absence. It is a region of space where gravity has become so intense that nothing, not light, not information, not any signal of any kind, can escape from within a particular boundary. That boundary is called the event horizon. It is not a physical surface. You would not feel yourself cross it, if you were falling inward. But once crossed, return is not possible. What enters does not come back. This is not mysticism. It is not poetry dressed in scientific language. It is a direct, mathematical consequence of general relativity, the same theory that describes the bending of starlight around the sun and the slowing of time near massive objects. A black hole is what happens when mass is compressed past a certain threshold, and the geometry of space itself curves so steeply that all paths lead inward. There is something worth resting with here. Even the most extreme endings in the life of a star, the supernova, the neutron star, the black hole, are not acts of waste. The supernova scatters elements across light years. The neutron star preserves, in its incredible density, a record of the physics that governed the star's final moments. And even a black hole, consuming everything that falls within its horizon, may radiate energy back into the universe over timescales so long they make the current age of the cosmos seem like an opening moment. Destruction and creation are, in the cosmos, the same gesture. The most violent ending seeds the most abundant beginning. And the material that is scattered, the carbon, the oxygen, the iron, the gold, does not disappear. It returns to the space between stars. It drifts. It mingles with fresh hydrogen. And in time, it becomes part of something new. If this kind of unhurried exploration is something you would like to return to, subscribing takes only a moment and helps ensure that more evenings like this one continue to find their way into the world. There is no urgency. There never is in this place. The material expelled by dying stars, whether through the gentle exhalation of a planetary nebula or the vast scattering of a supernova, does not vanish. It enters the interstellar medium, the thin, pervasive sea of gas and dust that fills the space between stars. And there, it mixes with the hydrogen that has been present since the earliest moments of the universe. This mixing is not incidental. It is the mechanism by which the universe grows more complex over time. The first generation of stars, called Population 3 by astronomers, formed from material that was almost entirely hydrogen and helium. These were the only elements available in the early universe. The Big Bang, in the minutes following the initial expansion, produced hydrogen, helium, and trace amounts of lithium. That was all. No carbon. No oxygen. No iron. No silicon. Nothing from which a rocky planet, a liquid ocean, or a living cell could be constructed. Those first stars are believed to have been very massive, very hot, and very short-lived. None of them survive today. They have never been directly observed, though astronomers search for their signatures in the oldest, most distant light the universe contains. What is known about them comes from models, from theory, and from the chemical fingerprints they left behind in the stars that came after them. Because when those first stars died, as supernovae, most likely, given their enormous masses, they scattered the first heavy elements into the cosmos. Carbon. Oxygen. Small amounts of heavier elements. For the first time, the interstellar medium contained something other than primordial hydrogen and helium. It was richer. Not by much. But by enough. The next generation of stars, Population 2, formed from this slightly enriched material. They were born in clouds that contained traces of carbon and oxygen and other elements that had not existed before. They lived their lives. They died their deaths. And when they did, they scattered still more heavy elements into space, adding to the growing inventory. In astronomy, the word metals carries a specific and somewhat unusual meaning. It refers to any element heavier than helium. Carbon is a metal. Oxygen is a metal. Iron, silicon, calcium, all metals, in the astronomer's vocabulary. This usage can feel counterintuitive, but it serves a purpose. It draws a clear line between the elements produced in the Big Bang, hydrogen and helium, and everything that came after, everything that required a star to exist before it could be made. The proportion of metals in a star is called its metallicity. And metallicity is, in effect, a measure of heritage. A star with low metallicity was born from relatively pristine material, early in the universe's history, before many generations of stars had lived and died. A star with high metallicity was born later, from material that had been through multiple cycles of stellar birth, death, and enrichment. The Sun is a Population 1 star, a member of the most metal-rich generation. It is estimated to be at least a third-generation star, meaning that at least 2 full cycles of stellar life and death occurred before it was born, each one adding new elements to the cloud from which it eventually formed. The Sun is not the first version of itself. It is an inheritor. The planets that orbit it, including Earth, are built from the accumulated gifts of previous stellar generations. The silicon in the rocks beneath your feet. The iron at the Earth's core. The water in every river, every ocean, every glass you have ever held. All of it was assembled from elements that were once inside stars that no longer exist. You are living on a world made of recycled starlight. This cycle, birth, burning, death, enrichment, rebirth, has been running for nearly 14 billion years. And it is still running now. Star-forming regions are visible across the galaxy today. The Orion Nebula, the Eagle Nebula, the Carina Nebula. In each of these places, clouds of gas and dust, enriched by the deaths of countless earlier stars, are collapsing under gravity, forming protostars, kindling new fusion reactions, and beginning the cycle again. The stars being born in these nurseries today are chemically richer than the Sun. They carry within them elements contributed by more generations of stars than the Sun ever knew. The universe is still composing itself, layer by layer, generation by generation. Each new star inherits the work of every star that came before it. There is a pattern in how the universe distributes these new stars. Many are born small, red dwarfs, dim and cool and extraordinarily long-lived. Fewer are born with moderate mass, like the Sun. And very few are born massive, the blue giants that burn bright and die young. This distribution, called the initial mass function, is remarkably consistent across different regions, different galaxies, and different epochs. Why the universe favors this particular distribution remains an open question. The pattern is clear. The reason beneath it is still being sought. A distribution of stars. Many small and faint. A moderate number of middling brightness. A rare few, brilliant and blue. The same pattern, repeated everywhere the universe makes stars. These open questions are not frustrations. They are invitations. They are the places where the story is still being written, not by narrators or writers, but by the stars themselves, and by the scientists who watch them with patient instruments and careful thought. There is a name for the era in which all of this is happening. Astronomers call it the stelliferous era, from the Latin for star-bearing. It is the age of stars. The period in cosmic history when the universe is alight, when stars are being born, living their lives, and dying their deaths in an ongoing, self-sustaining cycle of creation and enrichment. This era began a few 100 million years after the Big Bang, when the first stars ignited. It will continue for trillions of years into the future, far longer than the universe has existed so far. But it will not last forever. The rate of new star formation has already peaked. The cosmic supply of hydrogen, the raw fuel from which all stars are made, is slowly being consumed, converted into heavier elements, locked away in white dwarfs and neutron stars and black holes. Someday, inconceivably far in the future, the last star will form. It will burn through its fuel, probably very slowly, if it is a small red dwarf, and when it finally exhausts its hydrogen and fades to black, the stelliferous era will be over. But that time is so distant that it carries no weight as a concern. Trillions of years. Thousands of times longer than the current age of the universe. You are here now. In the bright time. In the age of light. And the stars are still burning. There is a philosophical thread that runs through all of this and is worth gathering together now, in the quiet of this late passage. Nothing in the universe is truly new. Everything is reassembled from what came before. The atoms in your hand have been part of multiple stars. Multiple clouds. Possibly multiple worlds. They are older than the Earth. Older than the Sun. Some of them, the hydrogen atoms, the ones that make up most of the water in your body, are older than any star that has ever existed. They were made in the first few minutes after the Big Bang, nearly 14 billion years ago, in the primordial nucleosynthesis that produced the universe's initial supply of hydrogen and helium. You carry that hydrogen within you now. Primordial matter. Atoms that have existed since the very beginning of everything. And alongside them, woven into the same body, are atoms of carbon that were forged in the core of a red giant. Atoms of oxygen assembled in the same stellar furnace. Atoms of iron produced in the last hours of a supergiant's collapse. Atoms of gold that may have been created in the collision of two neutron stars, an event so energetic that it briefly warped the fabric of spacetime itself, and then scattered across light-years of space before drifting into the cloud that would one day become this solar system, this planet, this moment. You are a meeting point of timescales. Ancient hydrogen and stellar carbon. Big Bang and supernova. The oldest material in existence and the products of processes that unfolded over billions of years of cosmic evolution, all woven together into a single form. A form that breathes. A form that wonders. A form that is, right now, resting quietly in the dark, listening to the story of the very processes that made it possible. You are not borrowing these atoms permanently. This is another quiet truth worth sitting with. When your life reaches its end, in its own time, in its own way, those atoms will return. To the soil. To the air. To the slow cycles of the earth. And on timescales almost too long to imagine, some of them may find their way back to the cosmos. Into new clouds. Into new stars. Into new worlds. The atoms do not belong to you. They are passing through you, as they have passed through other forms before, and will pass through other forms again. This is not a melancholy thought. It is a statement of continuity. The same continuity that has been running since the first star ignited in the young universe, nearly 14 billion years ago. Matter borrowed from the darkness, shaped into light, and returned to the darkness richer than before. That is the cycle. And you are part of it. Not as an observer watching from outside, but as a participant. A brief and conscious arrangement of the universe's own materials, resting tonight inside the story it has been telling itself since the beginning. If you have found something in this quiet place that feels worth returning to, the channel will be here. A subscription is a small thing, and it means these explorations will continue. There is no rush. There never is. And now the sky returns. The same sky that has always been there. The same stars, holding their positions, tracing the same slow arcs they have traced for as long as anyone has been watching. The constellations are unchanged. The patterns are the same ones that guided ancient sailors and marked the turning of seasons for civilizations that rose and fell and left only their star maps behind. Nothing about the sky looks different tonight. But something has shifted in what it means. Each of those points of light is a moment in a longer story. Some of the stars you see tonight are young, protostars that have only recently ignited, still surrounded by the remnants of their birth clouds, still settling into the balance that will define their main sequence lives. Some are in their prime, steady, patient, converting hydrogen to helium with a constancy that will persist for billions of years. Some are old, red giants swelling quietly in the dark, their cores contracting, their outer layers drifting outward, beginning the slow process of returning their materials to the space between stars. And some of the light arriving at your eyes tonight left its source a very long time ago. The star that emitted it may have already died. It may have already shed its outer layers, or exploded, or collapsed into a neutron star or a black hole. The light does not know this. It simply travels, at the speed physics allows, carrying the image of a star that may no longer exist. When you look at a distant star, you are not seeing the present. You are seeing the past. A message in light, dispatched years or centuries or millennia ago, arriving only now. The night sky is not a single moment. It is a collection of different moments, all arriving at once. A museum of different pasts, painted across the dark in light that has been traveling for as long as it needed to reach you. You have seen something of what lies behind each of those points of light tonight. The cold cloud. The slow collapse. The kindling of fusion. The long, patient burn. The swelling. The forging of elements. The gentle exhalation, or the generous explosion. The remnant, white dwarf or neutron star or black hole, holding its place in the dark. And the material, always the material, returning. Drifting back into the commons. Becoming part of the next cloud. The next star. The next world. It is a single, unbroken cycle. Matter gathered from the darkness, shaped into light, and returned to the darkness richer than before. It has been running for nearly 14 billion years. It will continue for trillions more. And you, resting here, breathing, made of exactly the same material, are inside it. There are things that remain unknown. There are always things that remain unknown, and this is not a cause for unease. It is the natural state of any honest inquiry into the workings of the universe. We do not fully understand how the most massive stars form. Stars above 8 or 10 solar masses radiate so intensely that their light should, in theory, blow away the very material trying to fall onto them. And yet, stars of 100 solar masses and more clearly exist. How they grow so large, whether through disk accretion, merging of smaller stars, or processes not yet identified, remains an active question. We do not fully understand the interior of a neutron star. The matter at its center exists under conditions that have no parallel anywhere else in the observable universe. It may take forms, quark matter, strange matter, exotic condensates, that have never been produced in any laboratory and may never be. We do not fully understand why the universe produces stars in the particular distribution of masses that it does. The pattern is consistent. The reason beneath it is still emerging. These are not failures. They are openings. They are the places where curiosity still has room to move, where the next generation of instruments and ideas may find something that changes the picture in ways no one currently expects. The story of stars is not finished. It is being written, still, by the stars themselves and by the patient effort of those who study them. And perhaps that is the most gently reassuring detail of all. The universe still has things to reveal. The questions are not exhausted. The answers are still arriving, at the pace they choose, in the way they choose, and the act of wondering, the simple, quiet act of lying still and thinking about where everything came from, is not diminished by what remains unknown. It may even be deepened by it. You are lying under a sky full of stars. Each one is a furnace. Each one is a factory. Each one is, in its own slow and luminous way, building the materials that future worlds will be made from. Some of those materials have already been built. Some of them are inside you, right now. The carbon. The oxygen. The iron. Assembled in stellar cores, scattered by stellar deaths, gathered into this planet, and organized by 4.5 billion years of chemistry and biology into a form that can look up and trace the whole story back to its beginning. The universe is not in a hurry. It never has been. Stars take millions of years to be born. They burn for billions. Their remnants cool for longer still. And the cycle that connects them, birth, burning, death, enrichment, rebirth, turns on a timescale so vast that the entire history of human civilization occupies less than a single heartbeat within it. There is time. There has always been time. The stars have been at this work for nearly 14 billion years, and they will continue for trillions more. The stelliferous era stretches ahead, long and luminous and unhurried, and you are here, now, resting inside it. In the bright time. In the age of light. Every breath draws in oxygen made inside a star. Every exhale returns stellar carbon to the air. The cycle continues, not only in the vast and distant nurseries of the galaxy, but here. In this room. In this body. In this quiet, ordinary act of breathing. You are not watching the cosmos from outside. You are the cosmos, resting. Made of it. Held within it. Breathing its materials in and out with every slow, unconscious breath. The stars that made your atoms are gone, but their work persists in you, in the ground beneath you, in the air around you, in every element heavier than hydrogen that you will ever touch. The story is still being told. The stars are still burning. The candles are still lit. And you, assembled from the generous remains of suns that completed their journeys long ago, are resting quietly in the middle of a universe that is still composing itself, still enriching itself, still, after all this time, finding new ways to turn the simplest element in existence into everything there is. That process does not require your attention to continue. It does not need you to understand it in order to proceed. But it is there, tonight, the same as it was last night, the same as it will be tomorrow. Steady. Patient. Ongoing. The stars are still here. So are you. And for now, that is more than enough. If something here has been worth resting with tonight, the comments are always open. There is never any rush. The channel will still be here whenever you return. For now, rest well. The stars will keep